Welcome to the session on LTE 1xEV-DO interworking. So let's see what we have as our agenda. And okay, so a brief introduction about myself. I graduated from Virginia Tech with a PhD in electrical engineering. As part of my PhD dissertation, I designed handoff algorithms using neural networks and fuzzy logic. I have worked for Nortel and Huawei, where I did the radio research management algorithm design for 1xEV-DO and UMTS products. I've been teaching for our solutions for almost 7 years, and the technologies I teach include, of course, LTE, computing technology, WiMAX, and other 3G technologies, UMTS, HSPA, HSPA+, and 1xEV-DO. Again, welcome to the session. Feel free to maximize the use of the Q&A box. We would also give you opportunities to ask questions using the audio bridge as well. Okay. So, what we plan to cover today, here are the main objectives for the session. So let's say we have a hybrid UE that supports LTE and 1xEV-DO. Then if you power up the device in the 1xEV-DO area, there is no LTE, then how do we carry out access? eHRPD is evolved high rate packet data, so evolved from 1xEV-DO. Then we will talk about the difference between main connection and auxiliary connection, that is for accessing 1xEV-DO. We have to do translation between 3GPP quality of service, LTE quality of service, and 1xEV-DO quality of service. So that would be between so-called QCI for LTE and flow ID for 1xEV-DO. So we'll talk about that mapping. How does the UE go between two technologies, LTE and eHRPD? So we'll talk about some coil flows. We would start using IPv6 between the PGW and 1xEV-DO network. So we'll briefly introduce so-called proxy mobile IPv6, and that's the mechanism we have chosen so that we can maintain IP connectivity without having UE to do anything special. So no client-based mobile IP. We are moving toward proxy mobile IP. So those are the topics we would cover today. So by the time we are done, you should have a very good foundation of how LTE and 1xEV-DO can work together. Go into the details. If you could let me know the kind of work that you are doing. I'll give you about 30 seconds. So Brenda, is my voice okay? Okay, hopefully you can hear me loud and clear. Any issue, let me know. Please participate in all the polls. We appreciate your feedback. Okay, so looks like about 30% system test integration, about 40 customer support, about quarter systems engineering. Okay, very good. What kind of details you are looking for? Okay, about 70% sort of focus on concepts and some details. Okay. Okay, 20% a lot of details. Okay, now we have normally tried to cover the medium degree of details, but if you want something more than what is being presented, please ask questions. Okay, let's get into the details now. Okay, so first of all, we would cover the architecture. So we would have connectivity between LTE and 1xEV-DO network. So we will talk about various nodes and the interfaces. So our focus is on the interworking between LTE and EHRPD, Evolved High Rate Packet Data. Now, forget about LTE for now. What is in general EHRPD? So EHRPD, Evolved HRPD. Now this HRPD, High Rate Packet Data, that is your traditional 1xEV-DO revision A, radio access network. That is your HRPD. Okay. Now, what is the meaning of evolved? So if you enhance the existing EV-DO radio access network, then it is evolved. And what kind of features does it support? Okay, it supports connectivity with the evolved packet core of LTE. See, normally what will happen is, let me draw a picture here. If I have EV-DO RNC, DO RNC, then that is connected to PTSN foreign agent. And that is connected to home agent. And here is the internet. That is the normal connectivity. Web servers such as CNN.com, things like that. Now, what we are saying here is that instead of connecting this DO to the traditional foreign agent, home agent type node, we would connect the 1xEV-DO network to evolved packet core. For example, we would, instead of using this home agent, we would start using PGW. So we would use PTSN, some kind of gateway, HRPD serving gateway, and now this is the new connectivity. So instead of using the old interfaces that you see with PTSN foreign agent, home agent, now we have started using LTE core network. So PGW is the one we have started using, and then we have the PCC architecture, policy and charging control. So we would start connecting to that as well. So basically, EHRPD supports connectivity with the PGW with the evolved packet core. Now, in an absolute sense, EHRPD may or may not support handover with EU-TRAN. Okay, this is the LTE radio network. But our interest in this session is interworking between the two technologies, LTE and EV-DO. So in our case, yes, we would have seamless mobility discussion for LTE, EHRPD mobility. So even though if you look at the definition, it doesn't have to support EU-TRAN in connectivity. But for all practical purposes, you would see that EHRPD indeed connects to the LTE network. We have the radio network enhanced. We have so-called packet control function. So that is normally in box as the RNC. So that's PCF. So we would have evolved elements like that. Formally speaking, EHRPD network itself does not include the serving gateway. Serving gateway is like core network element. So EHRPD network, radio network, connects to the HRPD serving gateway, and that connects to the EPC. So in summary, if you have your existing 1xEV-DO radio access network, and then you enhance those to understand the connectivity with EPC, specifically PGW, then that would be an example of an EHRPD network. So let's talk about that architecture that connects EHRPD with LTE. So on the top we have LTE network, and on the bottom we have EHRPD network, including the serving gateway. So we have the UE communicating with EV-DO base station. EV-DO base station connected to RNC, Evolved Access Network, RNC, and packet control function, normally in the same box. Now, RNC typically connects to the access network AAA server. There's the A12 interface. That's the normal interface, nothing new there. But this is new. The interface between RNC, that is evolved, and HRPD serving gateway. So HRPD serving gateway is the new network element that we have. Normally, what you might see in practice is you can upgrade PDSN and replace PDSN by HRPD serving gateway. That is the best way to look at this. So if you have HRPD serving gateway, then you do not need your regular PDSNs. You can replace existing PDSNs by HSGWs. That is that. Now we have this new node, which is replacement for the PDSN. We connect that to the PGW, and that interface between HSGW and PGW is S2A. That is the name of the interface, S2A. And on that interface, we support proxy mobile IP version 6. IPv6. So we have started using IPv6 here. So let's say we have a UE that is a hybrid UE which supports EV-DO and LTE. And now we want to do regular web browsing. This is the internet. So now the packets are coming from the outside world. They will arrive at the PGW. Remember, our UE is in the DO coverage area. This is the geographic area where our UE is. There is no LTE in that area. Maybe we are outside the LTE coverage area in some suburban or rural environment. So there is only 1xEV-DO available. So our user is connected to the 1xEV-DO radio network. So in that case, when the IP packet comes from the outside world, it is first arriving at the PGW. This is the LTE core network. From PGW, the packet would go to the HRPD serving gateway. From HRPD serving gateway to the RNC to the base station. and then over the DO air interface to the user. So this is how the user traffic is flowing when the user is in the 1xEV-DO coverage area. So as you can see, we have started using the LTE core network, even though we are using 1xEV-DO radio access network. We are no longer using PDSN, foreign agent, home agent. Right? So in that case, if the UE goes from one area to another, one HSDW to another HSDW, then we will be able to handle the mobility because PGW is still the anchor. PGW remains the anchor. So you can go between two HSDWs in EV-DO, or you can go from EV-DO to LTE. So either way, your PGW remains the same. Your IP address remains the same. So we have seamless mobility support. You can go between any two technologies, between any two HSDWs, and still maintain end-to-end IP connectivity for that UE. So that is the main use of this interface S2A, that we support the mobility, and it's IPv6 based interface S2A. Then we have this additional interface between SDW of LTE and HSDW. Now that is S103, and the reason for that is when we go from LTE to EV-DO, then we can do packet forwarding. So let me just draw a picture here so that it becomes clear. Okay, so we have UE talking to the LTE, internet, when the UE goes into the DO coverage area, then it will start talking to the DO system. So what we can do in that case is we can have the serving gateway forwarding the packets, whatever IP packet we might have got at the base station, they will be going to serving gateway, the RNC. So once the handover is completed, then we will be able to send those leftover packets to the user. So S103, it is optional, but if we have that, then we can have the packets forwarded to the DO technology. Once the handover is completed, packets P, QR, etc., then they will be sent to the UE once the handover is completed. So if we have that optional S103 interface implemented, then we would be able to forward the packet. It is a one-way packet forwarding from LTE to 1xEV-DO. If you go from EV-DO to LTE, that is not supported. There is no packet forwarding. From DO to LTE, there is one-way packet forwarding supported from LTE to EV-DO. That is that use of S103. Then we have the GXA interface between PCRF and HSDW. That is basically for QoS control. So if you remember, our LTE network utilizes so-called PCC, policy and charging control. And inside the PCC network, we have PCRF, policy and charging rules function, we have enforcement function, etc. So we want to control QoS using the help of PCC. So in case of user talking to the EV-DO technology, then we need to provide the quality of service rules to the EV-DO system. So how does that happen? PCRF is able to give the rules to the HSDW through GXA interface. That is the interface we have for QoS control. Then we have the regular AAA server or HSS, home subscriber server, is the database that has information about the user, and our HSDW will work with the AAA server so that we can do authentication and things like that. We'll talk more about that later. But basically, that is to support authentication. We have this S101 interface, very important. The S101 interface would be used to support handover signaling and so-called pre-registration. So when the UE is in the LTE network, then we will do so-called pre-registration. So MME and RNC would be communicating via S101 so that we can set up EV-DO session between the access terminal and the RNC, even though we are right now on the LTE interface. So pre-registration helps us exchange signaling between the access terminal and the 1xEV-DO RNC so that we set up the EV-DO session. We'll talk more about that. So that kind of signaling goes over here, and also handover signaling going from LTE to EV-DO. We need to exchange handover signaling messages. They go also over S101. So those are main interfaces that we have. So we talked about S101 interface. That's called pre-registration with EV-DO and handover from LTE to EV-DO. Then we have the S103 interface, that is for forwarding IP packets. And then we talked about that. S2A, that is the mobile IP tunnel, proxy mobile IP tunnel. So we can forward the packets to the user when user is using EV-DO system. That's the S2A interface. That. Okay. When the user is in LTE network, then the eNode would be sending out information related to EV-DO. For example, DO neighbor list. So eNode can send that out over the air to help handover to EV-DO in future. So those are some of the roles played by various existing LTE nodes and new EV-DO nodes such as HSDW. as we go through the remaining material, we will learn more about how the interfaces would be used. We have got several questions, so let's take care of those now. Can we have a mix of HSDW and PDSN? So you could have that. So you can gradually expand the use of connectivity with LTE. So yes, you could have that mix. But if the LTE coverage is available in a given area, then you should have HSDW. But if you have only DO coverage area and LTE is not going to be there for some time, then it is okay to have your regular PDSN. No problem. That is supported. S103, is it connecting SDW to PDSN or HSDW? Actually, if you look at S103, we are connecting that to the HSDW and HSDW to the RNC. We are not connecting SDW to PDSN. Okay, it is HSDW. Okay, that's because it is a EHRPD. So we have to use new network nodes. So it is HSDW. And what is the advantage of using S2A versus S103? What is used when? That is the question. Okay, let me draw a picture that will make things clear. Okay, so our UE is in EV-DO coverage area. Okay. So here is the UE, 1xEV-DO. Proxy mobile IP. The IP packets are coming from the outside world. So they would go to the PGW. From PGW over the S2 interface to the HSDW, then to the RNC, base station, all the way to the UE. This is the end-to-end connectivity. Now, let's say UE is moving from LTE to EV-DO. So what is happening right now, our UE is talking to the LTE system. Packets are coming from the outside world. So right now this is what is happening. UE is with the LTE system. And after a while, now UE moves to the EV-DO coverage area. So now what we would do, let's say we have some leftover packets. We have not yet sent those to the UE. So we would forward those to the serving gateway to the HSDW head. So now, those are the leftover packets, PQRS. So we have forwarded the packets to the target technology. So this is used S103 during the transition handover from LTE to EV-DO. And once the handover is completed, then we will have direct connectivity, meaning the newer packets would be going this way. So S103 is used only during the handover transition for packet forwarding. Once the handover is completed, once the UE and the 1xEV-DO system, they have successful communication between them, then there is no need for S103. Because the packets, new packets, are directly coming from the outside world over this S2A interface. So hopefully now it is clear when S2A is used and when S103. S103 only during transition from LTE to DO to do packet forwarding. That's it. Packet forwarding, nothing else. But once the handover is done, we do not need S103. We will tear down S103. It will be released, and then packet will directly go from PGW to HSDW and so on. Thank you for your questions. Anytime things are not clear, you want more details, please ask questions. Okay, so we talked about the roles played by various nodes. We talked about some interfaces. Let's look at interfaces a little bit closely. Okay, S2A interface. S2A. So that is here. So S2A is between the PGW and the HRPD serving gateway. So here we are showing both the control plane and the user plane. This is for signaling. User plane means for user traffic. So user traffic, basically we have GRE channel on S2A interface. This is the PGW. This is the HSDW site. And then when the packet is coming from the outside world, then it would be sending the packets to the HSDW using the GRE channel. That's the proxy mobile IP channel that we have used to encapsulate IP packets. So your original IP packet is, let's say, this. This is the original IP packet for the user. We would put that inside GRE tunnel. So basically we are putting one IP packet inside another IP packet, that is an encapsulation, IP encapsulation. So this is that tunneling. Once the HSDW receives that original IP packet through the tunnel, then it could be any kind of IP packet, could be IPv4 or could be IPv6, it does not matter. But basically we put that inside the, let's say, could be PPP between the UE HSDW, and then it will be sent to the RNC and so on. So now we have IP connectivity between UE and the HSDW. So S2A, basically we have GRE to forward the packets. Now what is this signaling? We have proxy mobile IP v6 being used. Proxy mobile IP v6. So we have PMIP tunnel, PMIP signaling between the HSDW and the PGW. So the idea here is that when the user goes from, let's say, one HSDW area to another HSDW area, so this would be like going from one packet zone, PDSN zone, to another packet zone, another PDSN, something like that. So normally in a traditional EV-DO system, because of the use of client-based mobile IP, we would be doing mobile IP registration, request, response, etc. So UE has to do that registration. So registration request and response, registration reply. So those are client mobile IP messages that you would have to use in traditional EV-DO system. But now we are moving away from that client-based mobile IP. We are using now proxy mobile IP. So in proxy mobile IP, our UE does not do anything. Okay? When the user goes from one HSDW area to another HSDW area, UE doesn't do anything. What we do is between the PGW and the HSDW, we have proxy mobile IP tunnel. So if the user goes from one HSDW to another, we would tear down the proxy mobile IP tunnel with the old HSDW and set up new HSDW PMIP tunnel. So UE has no role to play. So you can still maintain same IP address because PGW gave you the IP address, rather than sending the packet to the old HSDW1, our PGW is sending the IP packets to the new HSDW because we have set up the new proxy mobile IP tunnel. So the beauty of proxy mobile IP is that no impact on UE. UE doesn't even worry about that. UE just continues using its own IP address, but within the network, we are changing the tunnel. This is similar to what we do in traditional LTE, go from one serving gateway to another. We have S5 GTP tunnel, S5 based. We have new S5 with the new SDW. Similar to that, we have now GRE tunnel, proxy mobile IP tunnel between the HSDW and PGW, so that our UE does not have to worry about sending the traditional mobile IP registration messages, registration request, reply, etc. That is the idea. Let's take care of additional questions that we have got. How S103 is handled if the IP packets are coming from different e-node base to different UEs. Oh, we have UE specific GRE tunnel. We would have, let's say, one GRE tunnel for one user. We can have another GRE tunnel for another user. So this way, on the S103 interface, we have separate out packets for different UEs. Okay. So that's the answer to the question how S103 handles packets for different UEs. So basically, we would have to have different GRE channels for S103. In fact, let me see if I have that in the, okay. So just it's a GRE tunnel between the SZW and HSZW. So we will be able to separate out traffic for different UEs based on GRE tunnels. Okay, we have another question. During the handover, if the UE is connected to LTE, then while the handover is happening, what happens to the packet? Okay, so the user is moving from LTE to 1xEV-DO, then during the handover transition, what is happening to the packets? The packets would continue to flow to the e-node B. So let's go back to that picture. So during the handover transition, the packets are still going from PGW to the serving gateway e-node B, but now the UE is no longer using the air interface here, so it would be following this path. Okay. The IP packet is following this path. So from e-node B, it will go back to the serving gateway, and then through S103, it would go to the HRPD serving gateway RNC. So during the handover transition, the packets are forwarded and they are optional. Okay. So if there is no S103 interface, then we will have to drop those packets. Okay. But if there is S103, then we are able to forward those packets from SZW to the HSW all the way to the RNC. So RNC is buffering the packets. So during the handover transition, if S103 is supported, then all those IP packets are stored in the RNC. Once the handover is completed, RNC would be sending those packets to the UE. If there is no S103, then packets are dropped, and in that case, the TCP type retransmissions would occur between the UE and the web servers, let's say CNN.com or whatever the server you had for your EPS bearers. So hopefully your question is answered. Anytime the answer is not satisfactory, you want better explanation, you want more details, please ask follow-up questions. If I do not get a follow-up question, I would assume that you got your answer. One more question. Difference between the proxy mobile IP and GTP. And why GTP is not chosen in this case. Okay, so in general, the answer why GTP is not chosen. Okay, so the basic idea is the following. We could have chosen anything. Okay, that's the first thing. We could have chosen to use anything, GTP or proxy mobile IP. Now, GTP is defined by 3GPP. It has been there from GPRS edge time, 2.5G time. And then we enhanced that as far as the control plane is concerned for UMTS and then for LTE. So if we wanted, we could have chosen that, but 3GPP2 has chosen to use proxy mobile IP. Currently we have client-based mobile IP used between the UE and the PDSN for an agent and home agent. So probably it is an easier upgrade perhaps to upgrade the PDSN so that it understands now proxy mobile IP. Because the proxy mobile IP, you are trying to reuse the client mobile IP messages so that those messages are now between basically HSDW and PGW. So rather than HSDW exchanging mobile IP messages with the access terminal, it is exchanging those mobile IP messages with the PGW. So probably it is easier to go from the client mobile IP to proxy mobile IP from the EV-DO's perspective. So that's why probably we chose that. But in general, we could have chosen to support GTP as well. But probably it is a little easier to upgrade PDSN to understand proxy mobile IP because the messages are effectively reused. And the main difference between proxy mobile IP and GTP basically is just two different ways of supporting IP mobility. So GTP and proxy mobile IP. So this is IETF based. IETF defined and reuse client mobile IP messages. And GTP is 3GPP defined, you could say. 3GPP defined. If this is GTP, then we have tunnel endpoint ID here, tunnel endpoint ID here. And the protocol is GTP, GPRS tunneling protocol. But the idea is still the same. The original IP packet is encapsulated inside a GTP tunnel. And if it is a proxy mobile IP tunnel, then we will use the proxy mobile IP signaling to set up GRE tunnel. Again, we have header, GRE header, and that would identify the endpoints of that tunnel. So yes, PMAP is used to set up user plane GRE tunnel. Just a different format. And here in LTE, GTP version 2 for the control plane is used to set up user plane. It's just two different ways of doing essentially the same thing. One is just 3GPP defined, another one ITF. But other than that, no major difference. Okay. We could have chosen to go either way. Okay. Okay. So GRE. Okay, let's take a simple example. So today in EV-DO network, okay, we have, let's say, PDSN for an agent, and we have home agent, right? So we have this GRE tunnel between them. GRE tunnel. Okay. Because what we are doing is we are encapsulating. Okay, let's say this is GRE packet. Okay, IP packet, but it's GRE packet. So your source is home agent. Destination is PDSN for an agent. and inside that there is an IP packet for the user. So let's have that IP packet. So inside the user's IP packet, the source is, let's say, cnn.com. Destination is ABCD, which is the IP address of some access terminal, user equipment, ABCD. So the original IP packet that arrived from the outside world, let's say cnn.com, that is placed inside another IP packet, which is a GRE packet. It becomes a GRE packet because for the GRE packet, the source is home agent. Home agent is sending that IP packet to the destination, which is a PDSN. So here, when the packet reaches the PDSN, it will retrieve the original IP packet and send it to the RNC. That is the idea. Okay, so that's the GRE channel. Okay, so GRE channel is established between the home agent and the foreign agent today to support client-based mobile IP. That's what is done today. Okay. Now, in future, moving toward EHRPD, now the PDSN is not there. So we have HSDW talking in the PMIP language, PMIP signaling. It talks to the PGW, and using that we set up GRE tunnel for user traffic. Now we have this GRE tunnel for user traffic. So PMIP is a control protocol, right? Signaling protocol. And signaling messages that we would be using in PMIP, they are based on the client mobile IP, registration, request, reply type messages. So we are not reinventing the wheel. We are trying to reuse the existing messages. But now the UE doesn't have to worry about those signaling messages. Between the HSDW and PGW, we take care of the signaling. Okay. So that's the idea. Okay. And as far as the GTP is concerned, GTP version 2 control plane. This is the control plane. So GTP control plane protocol is GTP version 2 for the control plane. We will use that GTP2 version 2 control plane to set up the user plane tunnels. And again, they are GTP tunnels. So there is no PMIP here, no GRE here. Okay, and where do we use this? So one example is between LGW and the PGW. We use that. Another example is between eNode B and the serving gateway. Also, we use the GTP for the user traffic. Okay, so the question, GRE used by PMIP and GTP, so that is the answer. The GRE is used for the EV-DO scenarios between PDSN, foreign agent, home agent. That is the regular GRE channel that we have today to support the client-based mobile IP. Moving forward, when we have interworking between LTE and EV-DO, then GRE would be used between HRPD serving gateway and PGW. But GRE and proxy mobile IP, they have nothing to do with the GTP tunnel. GTP is completely separate, user plane and control plane protocol. Okay. Okay. So hopefully the use of GRE GTP is clear now. Thank you for your questions. One more interface that is of interest to us is DXA. So this is between the HRPD serving gateway and the PCRF. So basically what is happening is in EV-DO, when we want to provide quality of service, then we need to work with, think of this like upgraded PDSN. Then we have to work with the RNC and finally to the access terminal, user equipment, so that we can have QoS for that user. Now, we have decided that we will use PCC, Policy and Charging Control Architecture, for quality of service. So here, the PCRF, Policy and Charging Rules function, it will create quality of service rules, or so-called policy, and that is given to the HRPD serving gateway. HRPD serving gateway then works with RNC and finally UE so that we can provide that quality of service. For example, we would guarantee certain data rate, we would guarantee certain delay, things like that. Now, in eHRPD, the RNC is connected to the HSDW, which acts as bearer binding and event reporting function. Bearer binding and event reporting function. The PDF file that you have should have all the acronyms. So feel free to consult the file, or you can ask me for the acronym expansion. Basically, bearer binding, event reporting. Bearer binding. So we are binding the IP flows. For example, web browsing, email, those are IP flows. We will map that onto specific bearer. In LTE, we call that so-called EPS bearer, and in EV-DO, we will put that onto a specific flow. We will have a specific RLP flow. This is one RLP flow for email, another RLP flow, radio link protocol flow for web browsing, etc. So we are binding that IP flow onto a specific flow profile that is for QoS. I will give you some examples later. So RLP flow is associated with specific kind of flow profile, and that will give you quality of service. So if you have two applications that have similar QoS requirements, then we will give them similar profile ID, flow profile ID. If you have two different services with two different QoS requirements, then one RLP flow we will have one flow profile ID, another RLP flow we will have another flow profile ID. So in LTE we have QCIs, and in EV-DO we will have flow profile IDs. And there is some kind of mapping suggested in the standard, and I will give you some examples little later. But in summary, we have to bind our applications, our flows, to some kind of flow profile ID for QoS. So there is one function HSDW does, binding application to specific flow profile ID for QoS. Event reporting. So whenever some kind of events occur, it would report those events to the PCRF. So for example, the UE may initially be in LTE, but now the UE comes to EV-DO. So the event is change in the radio access technology. That now the UE has come to the EV-DO technology. There is one kind of event, and whenever that event occurs, then the HSDW will contact PCRF that, oh, now the user is using EV-DO technology and not LTE. So if you want to charge the user differently, If you want to modify QoS parameters, you can do those because the events are processed by PCRF to influence the policy in terms of QoS, in terms of charging. That GXA interface, basically QoS rules and figuring out what kind of policy you want to put. Should we allow that kind of application? Should we guarantee certain data rates? Things like that. So quality of service rules are specified using that interface, and events are generated and also conveyed on that interface. The protocol that we use is the diameter protocol. It runs over UDP, which is of course going over IP. So in summary, the GXA interface will help us with QoS implementation. Let's look at the interfaces. S101 here is between the MME and HRPD access network. This is RNC. So we have S101 application protocol. So that's the protocol that is in charge of S101. Now, there are two kinds of mobility scenarios between EUTRAN and eHRPD. We have optimized and non-optimized. So, optimized mobility between EUTRAN and eHRPD means that we have S101 in existence. S101 exists, it means we have optimized mobility between LTE and eHRP. No S101, meaning no optimized mobility. Okay, that is the key test to figure out whether you have optimized mobility between two technologies or non-optimized mobility between two technologies. So if there is S101, we know it is optimized mobility. Now, when we say optimized, what kind of optimizations we have? One is eHRPD pre-registration. So while on LTE, the UE communicates with EV-DO RNC using S101 to set up EV-DO session. So UE is only talking to LTE radio network E node B, MME, but MME will use the help of S101 protocol to send the EV-DO messages to the DO RNC, and that way we have communication indirectly between the UE and RNC. So we are using the help of S101 to set up EV-DO session. Why? Because in future, when we go to EV-DO area, we do not need to set up the EV-DO session. It is already there. So we will save precious time during the handover process for faster eventual handover. So that is the beauty of pre-registration. That even though we are on LTE right now, we set up EV-DO session between the access terminal and the RNC so that eventual handover is faster. Also, optimized handover signaling. So when the user goes from LTE to EV-DO, then we can exchange handover signaling so that the DO RNC reserves radio resources for the access terminal So we have resources already available and no need to worry about call blocking at that time. We can have faster handover. So in summary, S101 is useful to support optimized mobility. We can do pre-registration with eHRPD. We can do handover signaling exchange between EUTRAN and the eHRPD. Now, this is for one-way handover, one-way mobility from LTE to EV-DO. It's a one-way street. So if we do the other way, going from DO to LTE, then we do not use S101. Then there is no optimized mobility. It is always non-optimized. So going from EV-DO to LTE, there is no S101. We do not do any packet forwarding, no handover signaling, nothing of that nature. However, if you have LTE to 1xEV-DO mobility, then we have the S101 interface available for use. Let's take care of one more slide. S103, that is only for the packet forwarding. So when we go from LTE to eHRPD, then the packets are forwarded from CGW to the serving gateway to the HRPD serving gateway to the UE. If there are already some leftover packets at the E node B, then from E node B to the serving gateway to the HRPD through RNC. So during the handover transition, we can forward the packets, and the interface has nothing but our GRE tunnel. So we have serving gateway and HSCW GRE tunnel that will help us forward the packets. So that once the handover is completed, the RNC can send all those packets to the UE. Let's answer a couple of questions we have. If the UE requests quality of service after moving to eHRPD, HSW contact a PCRF or RNC for QoS. So once we are in the EV-DO coverage area, then all the new quality of service control is occurring using the help of PCC. So HSW and PCRF will communicate for quality of service. And then whatever QoS we decide by using the help of PCRF, then we need to request RNC. So HSW will request RNC. That PCRF has given me this rule. Do you have enough radio resources to support that QoS rule given by the PCRF? So we do need to get resources from the RNC, because RNC knows about the radio resources being utilized, but the rule itself was created by the PCRF. Another question, when the UE goes from one cell to another, does S101 keep track of UE location? If we just go from one cell to another, but you are still in the same zone, like packet zone, same packet zone area, then no need to worry about updating S101. When we go from one HSGW area to another HSGW area, right? Things like that, then we have to keep track of that, because maybe we have a change in the RNC. Right? So if there is a change in the RNC, change in the packet zone, so-called registration zone, you could say, it's called eHRPD registration zone. So it is traditionally PDSN type area, RNC PDSN area 1, RNC2 PDSN 2 area, like that. So if you go across the boundaries, yes, then we need to update our registration, because if you go to new RNC, then you need to get a new EV-DO session. Maybe you can transfer the old session to the new session by having inter-RNC communication. So that is okay. But we do need to have an update in case of change in the registration zone. But if you just stay within the same registration zone, then your session is valid. The only exception is we have to have 3 keep alive messages. So let's say our session is configured for default time 54 hours, and during the 54-hour session period, we will have 3 keep alive messages. So except for keep alive messages during the session, no need to worry about informing the network when we go from one cell to another. As long as you stay within the same packet zone, same registration zone, no need to worry about doing anything with the existing session. And since S101 is between the MME and the RNC, if your RNC is the same, your S101 remains the same. If you change RNC, then you need to have another S101 with the new RNC. But other than that, no need to worry about UE mobility. Okay, so those are the answers to your questions. Let me ask you a couple of questions before moving forward. So IP address, PDN is packet data network, IP address that we give the mobile device. Who anchors that? Who has given the UE IP address? I will give you 2-3 minutes to think about the question and answer the question. And please participate in the polls. Very easy. Think and click. But do not generate a random number, okay? The prerequisite is thinking. And it's an open book exam. So feel free to look at the PDF file that you have. And I will give you a hint. Even if there is no EV-DO, you are talking to LTE, then the same network node gives the IP address to the UE. So it does not matter what technology we are using, LTE or something else. This network element gives the IP address to the UE, regardless of the radio access technology. So that is my hint. Whether we are on LTE or EV-DO or UMTS or whatever, this network element anchors the IP address. It gives IP address to the UE. Okay, 30 seconds remaining. Okay, about 75% got it right. So it is PGW, PDN gateway, packet data network gateway, PGW. So yes, PGW is the one that gives IP address to the UE. So it does not matter whether we are using LTE or EV-DO, PGW anchors the IP address. One more question coming your way. So IP packets are forwarded during the handover, LTE to EV-DO handover, from serving gateway to what? So S103, it is between what? SGW and something from EV-DO side. And for the record, HSGW. HSGW means HRPD Serving Gateway. That is the full name for HSGW. HRPD Serving Gateway. HRPD High Rate Packet Data. That's EV-DO. I will give you 30 more seconds. And here I'm not worried about the final destination of the packet. I'm just worried about the other end of S103. The one end is, of course, serving gateway, SDW. What is the other end? Okay, let's share the results. Okay, about 70% got it right. So S103. So during the handover, serving gateway will use S103 to forward the packets to HRPD serving gateway. So S103 is between SGW and HRPD serving gateway, HSGW. And then HSGW will forward that to the RNC, eventually RNC to the UE through the base station. But HSW is the other end of that S103. So two ends of S103. One end is serving gateway and the other end is HRPD serving gateway, HSGW. Okay, let's have a short break. And then once we come back from the break, we will resume our discussion of interworking. So let's aim for 10 minutes. We have got one question through live meeting, but let me give you an opportunity of asking the question through the audio bridge if you choose to do that. *7 unmute, *6 mute. So this is your chance, *7 unmute. I will wait for a few seconds if anyone wants to use the audio bridge for questions. Okay, no question, then we'll just rely upon live meeting Q&A box for interaction. So please maximize the use of that. Okay, so the question is, does EPCF handle RNC functions and eNodeB handle EAN handle eNodeB functions? Let me draw a picture here. So here is the EV-DO base station. Base transceiver station here. Then we have RNC and we have PCF. This radio packet interface, RP radio packet. And then we have traditionally PDSN. Foreign agent and then home agent. This is connected to the internet. Okay. So if you want to compare this to the LTE technology, then DO base station is equivalent to LTE E node B, and DO RNC functions are also performed by LTE E node B. So if you combine the base station and the RNC together, that is equivalent to E node B in LTE. Because in EV-DO, the 7-layer protocol stack that is distributed between the base station and the RNC. And in LTE, we have physical MAC, RLC, PDCP, RRC, 2, 3, 4, 5-layer protocol stack that is all inside the E node B. So from the air interface perspective, LTE node B has all the protocol layers. But in EV-DO, the 7 layers that we have, they are distributed between the base station and the RNC. So physical layer all the way, so-called application layer. And the application layer has RLP, which is like RLC in LTE. So those 7 layers are distributed. And if you combine the two, this is access network. To upgrade that to understand LTE, that is evolved access network. So access network includes the base station and the RNC. Now there is so-called radio packet interface, A10 interface between PDSL and PCF. This is packet control function. So logically we have kept RNC and PCF sort of separate, but in real world, normally you would see this in the same cabinet. So typically, you would see that one box, one cabinet has both the RNC and also the PCF. So A8 you may or may not see. Okay, depends on the implementation. So from that perspective, RNC just talks to the PDSL directly via A10 interface. The packet control function is some kind of logical entity that provides the interface between the radio and the packet, which is the PDSL. So between the radio and the core network, it is some kind of logical interface. So that it just worries about the IP-based interface here, A10 interface. So we would have something like GRE tunnel between the PCF and the PDSL. But typically RNC implements PCF functions as well, same cabinet. So hopefully that is clear. Let's get back to our discussion of interworking. So we looked at the architecture, the interfaces between LTE and EV-DO. Let's look at some protocols in eHRPD. Okay. Now, in 1xEV-DO, the air interface has 7 layers. And I mentioned the low layer, physical layer, all the way up to application layer. So that's the EV-DO protocol stack. And to support interworking with LTE, we have introduced additional protocols. So air interface is on one side, 7 layers of air interface. And then in addition, there are additional protocols that we need to use, and those are the ones that we summarize here. PPP, point-to-point protocol. So in traditional EV-DO, we have logical connection between the EV-DO terminal, access terminal, and PDSL. And that logical connection is PPP connection, point-to-point protocol connection. So even when the UE is in the dormant mode, it does not have radio connection, it still has PPP connection. It still has the logical connection. So we can quickly get out of the dormant mode and start doing data transfer within half a second or so. So idle dormant transition into connected mode is very, very fast in EV-DO. So PPP is the logical connection between access terminal and PDSL. Think of that like some kind of EPS bearer connection between the UE and the PGW. It is that kind of connection, logical connection. It stays there for a long, long time, maybe 24 hours or so. So logical connection between ET PDSL, that is PPP. Now, we will use the help of the PPP protocol to negotiate use of other protocols such as IP. IP is extensible authentication protocol. So as part of the call set, we have to authenticate the device, authenticate the user. So to help us do that, we have so-called IP protocol, extensible authentication protocol, authentication and key agreement. So this is the protocol that we will use to exchange authentication related information. Now, we have to somehow negotiate that we will use this protocol to carry information on authentication. And the choice of that protocol for authentication related parameters transport, we have to use PPP protocol. So when we are setting up the call, as part of the PPP session setup, we will say, okay, let's use IP as the mechanism to carry authentication information. So PPP will be used to negotiate other protocols. Now we have also called vendor-specific network control protocol. We will use the help of that to allocate an IP address to the device. So remember, PGW gives IP address to the UE. But that IP address has to find its way from PGW to the UE, right? So from PGW to the UE, how do we get that IP address? In between, we have HRPD serving gateway, and HRPD serving gateway will use the help of vendor-specific network control protocol to convey the IP address to the UE. That's vendor-specific network control protocol, IP address allocation. And then there is a vendor-specific network protocol. So that is also between the HSVW and UE, so that we can carry the user traffic. Then we have RSVP, resource reservation protocol. So that will be used to help implement quality of service. Okay. So when you want to set up, let's say, some kind of IP flow that has a specific quality of service, then between the UE and the HSVW, we will use the reservation protocol to make sure that we meet the quality of service that is required for that IP flow. So that is the RSVP, reservation protocol. When we discuss the call setup, etc., the roles of various protocols would become clear, but we just wanted to give you an overview of what kind of protocols would be used to support interworking between the UE and the eHRPD LTE network. There will be changes to the air interface protocol as well, okay, to support interworking. But we have tried to minimize the impact on existing air interface protocol stack. We would introduce now a very important concept, so-called service connection. Now, there is so-called main service connection. Think of this like default barrel. It provides always-on experience. To the user. Okay. So let's say we power up the device, access terminal, then it would set up main service connection with the network. So we have radio connection between the access terminal and base station here. There's a radio connection. Then we have the station between the access terminal and the RNC. So radio connection, when you have the radio connection, the UE is in the connected mode, the active mode, and you can do data transfer, uplink, downlink. But in EV-DO, the connection comes and goes very, very quickly. So if you do not do any activity, no upload, no download for few seconds, the radio connection goes away. Now, a radio connection, similar in concept to the RRC connection that we have in LTE. When you have RRC connection LTE, you have identity called CRNTA. Cell Radio Network Temporary Identity given to the user. Similarly, in 1xEV-DO, when we have dedicated radio connection between the terminal and the access network, then we have MAC index given to the UE in a specific sector, one or more sectors. So that is the MAC index. So now we have the dedicated radio connection, but if you do not do data transfer, the connection goes away. And if you want to do data transfer again, you can quickly set up the connection within about half second. So very, very fast transition in EV-DO. Of course, LTE is even faster, 100 milliseconds is the delay from idle to the connected transition in LTE. But the EV-DO is reasonably fast, half second, 500 milliseconds. But then there is so-called session. Session is long-lived. So it may last for many, many hours, perhaps 54 hours. That is the default session duration in the standard. And the idea behind this session is that we can negotiate some parameters between the each access terminal and RNC, and we store those parameters as part of the DO session. So if the radio connection goes away, you can quickly set up the connection and start using those negotiated parameters. So the idea is that when we do power up, we would set up the session between access terminal and RNC so that now we have negotiated all the parameters. Because if you have a lot of parameters, it may take several seconds, maybe 4 to 7 seconds to negotiate a lot of protocols, negotiate a lot of parameters, power control parameters, RLP parameters, things like that. But once the parameters are all negotiated, we store them in the access terminal's memory, we store that in the RNC, so that in future we can start using those immediately. So connection can come and go, but the session is staying there for a long time, and we are able to use those session parameters without wasting time in doing the session negotiation again. So that's the idea behind separating a radio connection from the RNC session. RP is the radio packet session, between the RNC and the HSDW. For the traffic, we have A10 connection. And for the control plane for signaling messages, we have A11 interface. So let's say we power the device, then we would have connection between terminal and the network. We have the session between access terminal and the RNC. And then we also have radio and packet session between RNC and the HSDW. So earlier, we had A10 connection between RNC and the PDSN. But now, there is no PDSN, so we have to have A10 connection with the HSDW. So there's the difference between legacy DO technology and EHRPD. That in a EHRPD, we would have connectivity with the HSDW. So that is the A10 connection. Once connection session and radio packet session are there, we are able to set up the main connection because we would exchange PPP related messages. For example, between the access terminal and the HSDW, we have PPP connection. It's a logical connection, PPP, between access terminal and the HSDW. And what kind of PPP messages we would use? We would use PPP messages so that we can carry the IP messages for authentication. We can carry signaling messages to establish connectivity with the packet data networks. More specifically, PPP would carry vendor-specific network control protocol. We have configuration request response messages so that we can connect to, let's say, Verizon.com, AT&T.com, things like that. This is EV-DO, so VZW.com, maybe BlackBerry.net, things like that. We can connect to external networks, packet data networks. We will be able to use the same PPP connection to negotiate quality of service, and inside the PPP we will have chosen RSVP for reservation, and that would be helping us exchange signaling messages for QoS control. And finally, we can put users' IP packets inside the PPP frame. So PPP basically provides you some kind of framing structure. So inside the PPP frame, you can put IP messages, maybe you can put RSVP type messages, you can put user traffic, etc. So this is the main connection. So if you have the main connection, you can do best effort services, you can do email, web browsing, etc. So think of the main service connection as the default EPS bearer type connection, where you can do the best effort services. We have got one question. AAA, yes. So we got a question that is the authentication still using AAA server. So actually, there are two levels of authentication. So the one which is AAA, that is the same, and we'll talk about that briefly. So AAA, using A12 interface, so that is there, and then we have to authorize the subscriber for services, etc. So then AAA server will help us do that. But in LTE, we know we have HSS and MME taking care of authentication. In EV-DO, we will use HSS and AAA server for authentication, for services, user services. So we will use AAA server along with the HSS for authentication, etc. But there are two different levels. If you want to authenticate the device, ESN, for example, then we will have AN AAA authentication. So that is separate. And then authorizing the user for services, AAA server will be used. So that is the main service connection. Main service connection means we have the PPP established between access terminal and HSDW, and we have negotiated various protocols for carrying out different things such as authentication and QoS. Once you have the main connection, you can do regular web browsing email type service. Best effort service now possible. However, if you want to control QoS better, or maybe you want to combine best effort traffic for many different packet data networks, then we have so-called auxiliary service connection. So here we have several examples, and that will tell you different ways in which auxiliary service connections can be used. So let's say I have connectivity with two packet data networks, and then I want to use one application with one packet data network, another application, another packet data network. Let's say this is Verizon.com, 1xEV-DO.com, let's say. This is email, so let's say blackberry.net. So one packet data network, 1xEV-DO.com, another packet data network, blackberry.net. So here perhaps I am using web browser. One application, another application, email. So now we want to send those two different applications to two different networks, packet data networks. Now web browsing is like best effort service, so it's one IP flow best effort. Also email, we are not worried about latency, no guarantees of any data rate, so that is also best effort. So those are both best effort applications. So we can combine the two. We can multiplex both the applications, web browsing application packets and email packets, onto some RLP flow, and we will have specific A10 connection between the RNC and HSGW. And since we are combining multiplexing information for two PDNs, we will do the multiplexing based on the PDN index. So this may be PDN number 1, this may be PDN number 2. So we have multiplexed IP packets. One is a PDN1 IP packet, another IP packet PDN2. So we have used those two different PDN numbers to multiplex the traffic. And that traffic goes over this connection to the HSGW. And HSGW opens up that packet and says, oh, this is a packet for PDN1. So then it will forward that to packet data network 1. And it says, oh, this is another IP packet inside packet data network 2. So let me forward that to packet data network. So this is an example where we have used one auxiliary service connection to send information to two different packet data networks. So this is an example of auxiliary service connection 1. This is another auxiliary service connection 2. Auxiliary service connection 3. So let's look at number 2, auxiliary service connection 2. So here we have an application that has a specific quality of service. Okay. So that is assured forwarding. Okay. So better than best effort. It's another application. So we are sending that to the packet data network number 1. Observe that these are two different QoS requirements. Okay, so whenever you have different QoS requirements, you need different auxiliary connections. So think of auxiliary connections like your dedicated barrel. That you are able to control QoS in a much stringent fashion. So anytime we need something beyond best effort, we need a separate auxiliary service connection. So that is going this way, one RLP flow, another A10 connection between RNC and the HSEW, and that will find its way to the data network. The user is doing one more application, so this is now voice or IP. For voice or IP, we need even better quality of service control, expedited forwarding, so fast forwarding. The routers need to give high priority to this kind of service. Robust header compression, so we have to do that to minimize the overhead. That is going over another auxiliary service connection to the packet data network. So here the packet data network is number 2. So we will use that. Voice or IP application. So in this example, we have multiple applications with multiple DSCP code points for IP, QoS, and then we have different auxiliary connections to take care of different levels of quality of service. So in summary, auxiliary service connection we can use to multiplex traffic for multiple PDNs, and also anytime you need different QoS, you need a different auxiliary service connection. We have got one question. Can we put a lot of best effort onto the same main service connection? Yes. We can, let's say I have best effort service. Okay. Then I can put them on the main service connection. Yes. So if you want to do, let's say, email web browsing through a single packet data network, no problem. You can use here best effort. So best effort is possible for a PDN. So if you're connecting to just one packet data network and you want to put all those best effort applications onto that same PDN, no problem. Then we are able to use the main service connection. However, let's say you have multiple best effort applications that belong to different PDNs, their auxiliary connection will help you multiplex in a more efficient fashion. Okay? That is the idea. So if you want efficiency, if you want to have multiple connections with multiple packet data networks and all of them are having at least one best effort, then you can multiplex best effort traffic. Only if you want to multiplex from multiple packet data networks. But if you have a single packet data network, then it is good enough to have this main service connection so that you can take care of email and web browsing. Who will do the marking in terms of QoS? So whenever the packet needs to go to the IP network, okay, that node will have to do the mapping. So between, let's say, HSEW and the RNC, right, the HSEW would need to do that. Let's go to this connection. Yeah, so HSEW is sending IP packet to the RNC, so that will have to do that mapping. Right? The UE, when it creates an original packet, it could put some kind of DSCP inside, and that could be overwritten. If HSEW wants that, it can overwrite that. But HSEW is aware of that, and it is the main node that is in charge of DSCP type marking. Because for the downlink traffic, it goes from HSEW to the RNC PCF, and that is the IP connection. That's the IP network. A10 connection is there. So HSEW is the main one that will be doing the DSCP marking. But as part of the auxiliary service connection setup, We would exchange the information about the traffic flow template. We'll exchange information about what kind of QoS we want to give. So remember, the QoS rule is given by PCRF. PCRF gives the rules to the HSDW, and HSDW will propagate that to the radio network, RNC to be more specific. So we have some QoS policy coming from PCRF, but HSDW would be the main entity that would help us with DSCP marking for a specific QoS dictated by traffic flow template and other QoS parameters. Okay, so that's that. So in summary, main service connection is like a logical connection between UE and the HSDW. You can do PPP signaling, you can do best effort service. However, if you want to have strict QoS control, you need to have multiple auxiliary service connections. Also, if you want to multiplex traffic from multiple packet data networks, then you can do that also using that auxiliary service connection. So auxiliary service connection is basically helping you with better QoS control. Also multiplexing traffic across PDS. Okay, now we'll talk about various scenarios. So far we talked about the architecture, interfaces, and some terminology related to EV-DO, EHRPD. Now we'll talk about various scenarios, such as what happens when you power up the device in LTE. What happens if you go from LTE to EV-DO? What happens if you power up in EV-DO and then go to LTE? All those scenarios would be covered next. So first, we are talking about the UE powering up in LTE. Okay, now we know this, that if the UE powers up in LTE, it has to do the attach operation, right? So basically, you have to do synchronization with the LTE system. You have to set up the RRC connection between the UE and the E node B in a given LTE cell, and then the UE sends attach request message. So using that RRC connection, the UE sends attach request. Now, who should process attach request? E node B or MME? So, question for you. You can answer through Q&A. Who processes attach request coming from the UE? Who is responsible to authenticate UE? E node B or MME? Okay, we got two answers. Very good. MME. So yes, MME. So MME would be processing the attach request message, and it will work with the HSS. So that's what is happening here. The attach request is forwarded to the MME, and now the MME will work with the HSS so that MME can authenticate the UE. Also in LTE, we have mutual authentication. If you recall, UE authenticates the network, network authenticates the UE. So let's say that part is done. The authentication is done. Next, we want to set up default EPS pair. Now, default EPS pair, it has three logical links. Do you remember those? Default EPS bearer has three logical links. What are those three logical links? What constitutes an EPS bearer? There are three things inside the EPS bearer. What are those three logical links? So I will wait for a few seconds. Okay, air interface. I got one answer. Air interface S1 and S5. Very good. So we have air interface between the UE and the E node B. That is called the radio bearer, data radio bearer. That's the radio bearer. And then we have S1 user plane. And finally we have S5. So those three together constitute an overall EPS bearer. So it means that we have to figure out who the serving gateway should be and who the PGW should be. So if you recall, the serving gateway selection is based on location. So if the UE is in Dallas, we would pick a serving gateway in Dallas. If the UE is in Chicago, a serving gateway close to Chicago will be selected. How do we pick the PGW? PGW selection is based on the access point name. Let's say this is a Verizon subscriber, so vzw.com is the access point name, and some PGW would be in charge of that. vzw.com access point name. So PGW is selected based on access point name, and the serving gateway is selected based on the UE location. So MME selects both the serving gateway and the PGW based on those criteria. Now, once the SGW PGW is selected, we are able to proceed further and set up the radio bearer, the S1 user plane, and S5. And that means now we have end-to-end bearer setup. Once the bearer is set up, normally during the default bearer setup, the IP address is allocated to the user as well, and typically the PGW is the one that allocates the IP address to the UE. The PGW allocates IP address to the UE, and it is formally conveyed to the UE by MME in the attach accept message. So when the MME sends attach accept, to respond to the attach request, then the IP address would be allocated as part of that message. So in summary, after power up, in LTE network area, we have done the attach operation. So we have now always on experience because we set up the default EPS bearer. The UE may have additional bearers established too. Okay, depends on what the UE is trying to do. But we would have at least the default EPS bearer and one or more dedicated EPS bearers as well. Now here is the idea. If you recall, there is S101 interface. So I have MME and I have RNC. Right? That is this S101 interface between the MME and RNC. And we say that one of the things we can do is so-called pre-registration, EHRPD pre-registration. We can have communication with the RNC and set up EV-DO sessions while we are still in the LTE coverage area. So to help us do that, we have so-called the concept of tunneling. What is tunneling? Tunneling very simple. Let's say I want to send some HRPD message, whatever that message is, connection request or traffic channel assignment or whatever that message is. That HRPD message is placed inside an RRC signaling message. For example, uplink, downlink, information transfer. So over the air interface, we put our HRPD message inside some RRC message. And when the eNode B gets that message, it will forward that message to the MME using S1 application protocol message. So that is encapsulated inside S1 AP because the MME and the eNode B, they have S1 interface that is controlled by this protocol, S1 application protocol. So we put the HRPD message inside S1 AP message. Okay, so that's again encapsulation. So now MME gets the original HRPD message and puts that inside some S101 message. And S101 application protocol is in charge of that S101 interface. So as you can see, we can have communication between the UE and the RNC through tunneling. So E node B transparently lets the message pass through, MME lets the messages pass through, and we are using the RRC connection over air interface. We are using S1 MME interface between E node B MME, and we are using this new interface that we have defined for interworking between LTE and EV-DO, that is S101. However, remember, this is optimized mobility. So if there is no optimized mobility, there is no S101. Okay? So here we are discussing the mobility scenario in future that would be helping us make the handover process much faster. So we are tunneling the HRPD messages using these RRC uplink, downlink information transfer. We have S1AP transport of signaling messages and S101. That is the key. So eventually, when the user indeed goes to EV-DO technology area, then we can do faster handover because you have already set up the session through this pre-registration process. So here we are mentioning that this pre-registration is like making reservation for your flight several months in advance. So when you want to fly, everything is all in place. Just need to print the boarding pass and you are all set. Okay, that is the tunneling of CDMA 2000 message. Now if you read the standard, CDMA 2000 basically applies to both 1X and 1xEV-DO. So CDMA 2000 in the LTE standard refers to both 1X and EV-DO. Here we will be discussing EV-DO. Okay, so now we know how the messages can go between the access terminal and the RNC. The kind of messages that we want to exchange are related to so-called pre-registration. So let's discuss the overall scenario for pre-registration. Okay, so we have the UE communicating with the LTE network. So assume that LTE attach is already done. So UE has already completed the attach operation. And then the E node B has conveyed to the UE as part of system information block number 8 that pre-registration is required. EHRPD pre-registration is required. That indicator comes on system information block number 8. So now the UE looks at that pre-registration requirement and says, oh, now I need to communicate with the DO RNC because this E node B is telling me that I am supposed to do the pre-registration with EHRPD. So then it will start sending out HRPD messages, and the message will find their way to the RNC. So we set up the session between the UE and the RNC. Now let me ask you a question and refresh your memory. As part of the session setup, RNC allocates some kind of identity to the UE. What is the name of that identity? So, I will repeat my question. When the UE has a session with RNC, that RNC allocates some identity to the UE. The identity starts with U. Oh, I already got the answer. UATI, very good. Thank you for your answer. UATI, very good. So every UE that has an EV-DO session with the RNC has been allocated UATI. Thank you for your answers. So that's what we would do. We would set up the session, negotiate all kinds of parameters, power control parameters, RLC parameters, etc. And we allocate this UATI also. And we can do authentication. Someone asked a question about authentication. So if you want to authenticate the device, the hardware, let's say ESN or whatever, then you can do that by having message exchange between UE and the PCF, RNC and AAA server. There is a A12 interface, and maybe I should put another. We have between RNC and there is some server called AN AAA, Access Network AAA. So we can use the help of that to do device authentication. So if you want to make sure that the hardware is the valid one, then you can do that. Typically, this could be combined with the regular AAA server. In practice, but logically it's a separate entity. So let's say we authenticate the device, ESN is the valid one. Then between the UE and the HSCW, we set a PPP connection, point-to-point protocol, in the main A10 connection. Remember, we have main service connection, auxiliary service connection. So at this point during the presentation, first we are setting up the main connection. So there is A10 connection, and we would decide that, okay, let's use IP, extensible authentication protocol, to convey authentication parameters. So we choose that here, and now we start exchanging IP messages between the UE and the HSCW, between HSCW and the AAA server. So once those messages are exchanged, then we have taken care of the authentication process. Once the authentication is done, then we would have partial PDM connection. Partial, not complete. Why? Because remember, the UE is right now with the LTE system. So the UE already has those connections. We have data radio bearer with the E-Node B, with the serving gateway, S1 user plane here. Then we have PGW, S5, S8. So we are already having those logical connections. Okay? And we are able to communicate with the outside world. So we want to have only partial connectivity. Full connectivity means that HSDW and PGW, they are connected for that UE. So right now we do not want to connect our HSDW with the PGW, because then PGW will be confused where to send the packet. Should it send the packet to the serving gateway or HRPD serving gateway? So that's why we do not want to have that connection right now. Okay? That's why we say that it is an example of partial PDN connections. Okay, we are only partially setting up the PDN connection. So we will have connectivity all the way between the UE and HSDW, so that in the future, when the user really goes to EV-DO, then we can quickly set up the remaining last connection, and then we can do the data transfer. So we are setting up everything else in anticipation of a future handover to EV-DO to accelerate that process of handover. So we set up the partial connections, and we also indicate to the HSDW that, oh, by the way, this is like handover type attach. Okay. And then if we need to have certain dedicated barriers that need reservation of resources, then we can do that. Basically, we are setting up the GR Ethernet, A10 connections, those things ahead of the time, flow IDs for our RLP flows, etc., so that we do not waste our time in future. So we basically set up the required PDN connections, barriers, etc. And in case our user goes from one RNC to another, then we have to basically change our anchor for the RNC session. So in that case, we would have to make sure that we are able to maintain the EV-DO session. That is another mobility aspect here. So maintenance meaning periodic messages. So once you have the DO session, there will be 3 keep alive messages because the timer would expire, and then we have to do session update just to make sure that network knows that we are still alive and well. So that's keep alive, so that's maintaining session. If you go from one RNC to another, you have to, of course, move the session to a new RNC. So basically, at this point, our HSDW knows about the UE, and we have all the connections, logical connections set up between the UE all the way HSDW. Now we have got a couple of questions in the line, so let's take care of those. Okay, will we talk about EV-DO and EHRPD? Now, our goal for this session is interworking between LTE and EHRPD. Okay. If you just have normal EV-DO and EHRPD, that is not covered in the session. But it would be not so seamless because if it is just EV-DO, then we would have client mobile IP and so on. Then it will be sort of you have to break the IP connectivity. So it will not be so seamless. So it's not covered here, but send me email and I will give you some references. Okay. But the standard is moving toward EHRPD. The operators are moving toward EHRPD. So, as I said, the benefit of EHRPD is that now the PGW anchors the IP address. So, regardless of where you are, you can maintain the same IP address. If you have just EV-DO and you're connected with PDSN, front agent, home agent, and then is difficult to make it work with EHRPD. The reason that you want to go for EHRPD is to maintain seamless mobility. Okay. But if you have anything else, let's see how much time we have, and I would see if we can talk about that. But it will not be seamless mobility. The operators are upgrading their networks to support EHRPD so that we don't have to worry about this. For pure EV-DO and EHRPD, then yeah, we will not have seamless connectivity. you would have to basically restart your connection. Okay, let's have a couple of poll questions. So when we are using the eHRPD network, are we using IP protocol for authentication? Thirty more seconds. Okay, almost all of you gave the correct answer. So basically, for our new device that supports LTE and EV-DO, eHRPD, that will use IP protocol for authentication, because now the IP messages will be going between the UE and the HSGW. HSGW will work with the AAA server. So yes, IP aka would be used for authentication. Let's go to the second question. I will give you 2-3 minutes for this question. Yeah, and sorry about this. We have 2 correct answers. So do not worry about that. If you pick one of the 2, that is okay. Oh, actually, no, there is only one correct answer. I just misread it. In the original version of the standard, we had optimized handover from LTE to EV-DO and also EV-DO to LTE. But then we removed the optimized handover from DO to LTE. So we removed that. Okay, so it is no longer supported in the standard. Okay. So the optimized handover, optimized mobility is only from LTE to EV-DO. From LTE to EV-DO, eHRPD. There is only one way optimized mobility, one way. So there is only one correct answer now, okay, based on the latest version of the standard. Earlier we had 2 correct answers, but now there is only one correct answer. I'll give you 1 more minute. Okay, let's discuss this question. So during the pre-registration, basically we are setting up the session between the access terminal and RNC. Now, when you are doing the pre-registration, we are still using the LTE radio network. So over the air, we are using RRC connection. So let's go to that slide here. So over the air, we are using RRC messages to forward the eVideo message. In node B, we'll use the S1 MME interface to forward message to the MME, and MME connects to the RNC via S101. So we are using LTE radio network. We are using S1 MME and S101. So we use all those interfaces to negotiate eVideo session. And the idea here is that if you set up the session now, in future, when the UE goes from LTE to eHRPD, we can do faster handover because the session is already there. If there is no optimized mobility, no S101, then when the UE goes from LTE to DO, we have to do all the session setup from scratch. It will take several seconds. So we lose precious time during that handover. And to minimize the handover delay from LTE to DO, we want to do pre-registration. That is the main idea. So yes, we want to use S101. Yes, we are using LTE air interface. We are not using DO air interface. We are not talking to DO base station. We are talking to LTE E node B. And it has nothing to do with DO to LTE handover. So when the users go from eHRPD to LTE, we do not use S101. S101 is for one-way mobility, one-way optimized mobility from LTE to eHRPD. It is not used the other way, meaning from eHRPD to LTE, we do not use S101. Okay. In fact, there is no optimized mobility from eHRPD to LTE. Okay, so we got one question. Now the operator has eVideo. Then they have to migrate to eHRPD and then LTE. That is correct. And if the movement from eVideo to eHRPD is not seamless, what is the advantage of moving to eHRPD? See, here is the basic idea. We want to ensure seamless mobility between LTE and 1xEV-DO. So, we would upgrade our network such that we have enhanced RNC, Evolved Access Network, that can talk to HRPD serving gateway, a new node. So you can get rid of your existing PDSNs and just have HSDWs. So for an old eVideo only device, HSDW acts like PDSN. And for a new hybrid device that suppose LTE and eVideo, eHRPD, then it would act as HSDW. So the idea behind HSDW and eHRPD is that we can maintain the same IP address. So if you upgrade the network, meaning you have HSDW and you have evolved RNC, then you have seamless mobility. You have same IP address because the IP address is now allocated by the PGW. So whether you are using eVideo air interface or you are using LTE air interface, you have same IP address. So the advantage of moving to eHRPD is that you have now connectivity with the evolved packet core, more specifically PGW at the minimum, so that you have IP connectivity. You can maintain that IP address regardless of what radio access technology you are using. That is the benefit. So if you stay with eVideo and you do not upgrade your RNC, you do not use HSDW, then the problem is that in eVideo you got IP address from home agent, and you go from one area to another, you have to do client mobile IP. But if you go to LTE coverage area, then you have to do everything from scratch. So you lose the IP connectivity. Okay? So in summary, the benefit of going to eHRPD and having HSCW is seamless IP mobility, even when you go across technologies such as LTE and eHRPD, 1xEV-DO. So yes, essentially, to get good performance, operators indeed have to use eHRPD. So if they do not want to do optimized mobility, it is okay. If they do not want to have S101, it is okay. It will work because you will still have PGW giving the IP address. Okay? So if there is no S101, there is no optimized mobility. There will be non-optimized mobility. Still, you have the same IP address because PGW will connect to the HSCW connecting to the UE through radio network. So S101 will improve the performance because you have negotiated session. So your LTE to DO handover will be much better. However, if you do not want to do that, if you're okay tolerating few seconds of delay from LTE to DO handover, then it's okay. You do not need S101, but you still have HSCW talking to the PGW. So for LTE HRPD interworking, you need to have HRPD serving gateway. You need to have the S2A interface between the HSCW and PGW because you want the PGW to be the anchor regardless of what technology the UE is using, LTE or eHRPD. Okay, we have a couple of questions coming here. Let's take care of those. If part is EV-DO and part eHRPD, then will there be call drops? Yes. You would lose IP connectivity. Correct. But at least you will have HSCW. If not S101, I should have at least HSCW. Okay? But yes, if you have pure RNC, DO RNC, and they talk to PDS and foreign agent, home agent, yes, then there would be loss in IP connectivity. Yes, there will be so-called call drops. Correct. And we have one more question. If each UE to do pre-registration, is there any criteria to do pre-registration? Yes, good question. So the question is, can we do some kind of prioritization? Do we have all eNode Bs required to do pre-registration, or maybe only some UEs that are talking to the eNode B in the border area, only they need to do pre-registration? Okay. So let's say we have put LTE in a specific area, okay, and we are right in the core of the LTE coverage area. So this is all LTE. These are all eNode Bs. And now some eNode B, let's say, toward the border. Basically here, this is DO only. Yeah, so it is possible that we can activate pre-registration here. That would be a good idea so that we minimize the pre-registration traffic. So inside the core, let's say here, may not need pre-registration. So what you asked is completely valid, perfectly valid. You may not need to do that in the core sites or on the border sites that are next to the EV-DO coverage area. So probably you can activate pre-registration there. But I would do 1 or 2 tiers. So having just 1 tier is a little bit risky. So I would do 2 tiers like that perhaps. So that if the user is moving fast, you still have some cushion in terms of time. Okay, but very good point. So in summary, it is not required to have pre-registration activated in every single eNodeB. Maybe toward the border region, we can activate that. Very good. Okay. Again, anytime you want more details, more explanation, just let me know. Okay. So basically, S101 will make your eventual handover faster, okay, for optimized mobility. So it is required only for optimized mobility. And to do pre-registration, we have to have S101, otherwise we cannot do pre-registration. And it enables AU-TRAN to LTE handover faster. Not this way. This is not supported anyway in the standard right now. So there is no optimized mobility from LTE to EHF. In the standard today, we have optimized mobility only from LTE to EV-DO. Okay. So that's that. Okay. So what has happened so far? Our UE was in LTE coverage area, and we did the LTE attach operation. We did pre-registration with the EV-DO system. And now, let's say the user moves, then we have to basically do the handover. So we will talk about that scenario now. Okay. Now, in general, when we go from LTE to EV-DO, how do we know that we have some EV-DO available in that coverage area or not? So the standard has so-called system information block number 8, SIB8. And SIB8 is helping us do the cell reselection to a new technology. So it would say, for example, whether pre-registration with EHF is required or not, and if it is required, then what is the zone ID. So this is the registration zone, packet zone. So let's say one RNC area, one color code, another RNC, another color code. So you may want to do zones based on that, so that if the UE goes from one RNC zone to another RNC zone, you want to have session transferred from old RNC to the new RNC. So that is the use of that zone ID. And then whether you should indeed go to HRPD or not, there will be some cell reselection thresholds. So for example, it would say that RSRP from LTE, let's say, drops below minus 90 dBm, and EV-DO EC or I0 for some pilot PN offset is greater than, let's say, minus 8 dB, something like that. So you can provide those kinds of thresholds as part of the cell reselection threshold in SIB8. We can provide the neighbor list, what carrier frequencies are available, what are the pilot PN offset for EV-DO. Those kinds of parameters are also given in SIB number 8. So now you know that, okay, in that neighborhood we have pilot PN offset, let's say 100, 104, 108, those are available. So the UE can look for those 1xEV-DO sectors when it has time to look for those. That is SIB number 8, very, very important. Now, there is one way the UE can get the information about EV-DO neighborhood. So when the UE is in the connected or idle mode in LTE, it can get that information. Also, if the UE is in the connected mode, then eNode B can send a message such as RRC connection reconfiguration, and as part of that also we can provide similar information, frequency, PN offset, etc. Now if the UE is in the connected mode, then the UE is busy all the time. It is looking at every subframe to check if eNode B has given any resources or not. So if the UE is busy all the time, UE has no time to look for EV-DO neighbors. So that's why we have some kind of gap, measurement gap. So we have on time, off time. So during the off time, the UE is on LTE, and when the gap is activated, then here the UE can look for EV-DO. So during certain time period, the UE has a time off from the LTE interface, and it can look for other technologies such as EV-DO. So during the measurement gap, the eNode B will not send any packet to the UE because the UE is no longer an LTE interface during those intervals. It is on the EV-DO technology looking for some pilots. So we can specify when to start the gap pattern, when, how many subframes, during which subframe there is a gap. The pattern is on time, off time, there is the pattern here. What terminal should measure maybe pilot strength for EV-DO, how terminal should do the averaging of EC or I0 measurements, that is specified. And let's say the UE measures a strong EV-DO sector, then when should it report the measurement to the LTE network? There are two events defined, events B1 and B2. So event B1 says that when EV-DO neighbor becomes better than certain EC or I0, let's say this is minus 8 dB, minus 9 dB, then UE says, oh, event B1 has occurred, and then it will send a measurement report message to the LTE eNode B, so eNode B can make the handover decision. Similarly, there is another event, event B2. It says that LTE RSRP, RSRQ drops below some threshold, and the LTE neighboring technology such as EV-DO, so that neighbor is able to give quality that is better than some other threshold. So this would be EC or I0 for EV-DO. So EV-DO is becoming better than a threshold, and LTE is becoming weaker, then there's called event B2. So our eNode B can configure the UE with those events and thresholds B1, B2, and when those events occur, the UE would send a measurement report message to the LTE eNode B summarizing the RSRP, EC or I0 measurement, so that eNode B can decide should the UE stay here with LTE or we should ask UE to go to the DO technology. And then there are some call flows coming up, but let's have a short break, and once we come back from the break, we will talk about signaling for handover. So let's have a 10-minute break. And then we would resume with discussion on handover signaling flow. Okay, no questions for audio bridge, then we will keep moving forward. Please submit your questions through Q&A box. Okay, so currently the UE is with LTE network, and it is in the connected mode. So we have RRC connection. We have configured the UE to make measurements using events B1, B2. Maybe you will have one of those events satisfied, and then UE sends measurement report. So as part of the measurement report, the EU is indicating EC or I0 for EV-DO and also RSRP for LTE cell. And now the E node B has the handover algorithm. So it makes the handover decision that yes, the time for UE to go to eHRPD, because LTE cannot give good quality signal, and the UE is moving away from LTE into the EV-DO coverage area. So it sends handover from EU to preparation request, and it says, okay, the target technology is HRPD. So the UE then prepares the EV-DO message connection request, route update message indicating that is or I not value. So we send that to the E node B. Now see, this message is sent over LTE air interface. We are using that RRC connection here. So this is tunneling, and the message is then tunneled to the MME on the S1 MME interface through the message called uplink S1 CDMA 2000 signal. So that is S1 AP message. Then we have S101 application protocol. So that's the direct transfer request message. Inside the direct transfer, we are putting that HRPD connection request message. The E node B tells the MME which sector. Let's say this was for sector with PN offset 100. So we say that pilot PN offset for PN offset 100, whichever is the identity of the sector, we indicate that identity X. And now the MME says, okay, who is in charge of EV-DO sector X? So then it has some kind of database, some table. It says if the sector identity is X, maybe RNC number 3 is responsible for that. We are now talking to RNC number 3. We have S101 direct transfer request going to RNC number 3, and we indicate who the PGW is for that UE, because what would happen is we would have to communicate with the PGW so that in future PGW sends traffic to the EV-DO system through HSDW. So that's why we need to indicate which PGW is in charge of the UE. And to send the packets in the uplink to the PGW, we would need GRE keys, okay, for that. Because remember, between the HSDW, PGW, we would have the GRE tunnel. Okay. So we need to indicate the uplink GRE key. So that we can send the IP packets to the correct PGW. So that's the GRE key. And now we have to register with the HSDW. So as part of the A11 registration request message, A11, that is the signaling interface between the RNC and HSDW, because PCF and RNC, they are in the same box. So A11 interface is sending the registration request. Inside that we put the IP address that we got and the GRE keys for packet forwarding. So let's say we support packet forwarding from serving gateway to the HSDW, right? So the S103 GRE packets would be going from serving gateway. Okay, so we are including information for S103, and then RNC. In the meantime, would have to check, do I have enough resources available to support that handover? So assuming that we have resources available for handover, then we are moving forward with the handover signaling. RNC would tell the MME that okay, the resources have been reserved and the resources are specified in the traffic channel assignment message. So for example, we would indicate that for pilot PN offset 100, right, we are giving MAC index number 20, for example, to the user. That is the identity of the dedicated radio connection between the UA and the sector. And of course, HRPD serving gateway's IP address and GRE keys we need for packet forwarding. So that information is sent to the MME. MME will tell the E node B that please forward this message, traffic channel assignment message, to the UE. So that finds its way to the UE. So S1 MME, it is the tunneling, CDMA 2000 tunneling, and over the air RRC message is mobility from EUTRAN command. So mobility from EUTRAN, that is the handover command asking the UE to go to a specific DO specific technology. So in this case, this EV-DO technology, and traffic channel assignment would identify what PN sector we have, what resources we got inside that sector. At this point, the UE leaves the LTE interface and it starts communicating with DO base station and then DO RNC. Now it has got a traffic channel assignment message, so the response to that is traffic channel complete, TCC. That is your message. So that is an acknowledgement that we have received the traffic channel assignment message. Once the RNC has received the TCC, we have successfully established an interface communication between the UE and the EHRPD network. In the meantime, we have to prepare for packet forwarding, and that is the reason that we have the IP address and the tunnel endpoint ID for packet forwarding. So using this eNode B is forwarding packets to the serving gateway using the tunnel endpoint ID on the SDW side. The SDW will be sending that to the HSDW. That would be the GRE key X103. So we will use this information for that. And then RNC will be buffering the packets until the handover is completed. So now the radio interface is okay between the UE and the EV-DO RNC. So we have to tell the PGW, please do not send packets to the old serving gateway. Send the packets to me. That's what HSDW is telling the PGW, proxy binding. So this is PMIP signaling, proxy binding up proxy binding update is sent this way, and acknowledgement, proxy binding acknowledgement going this way. So now we have informed the PGW that please update your binding and send the packet to me in future. So once that is done, the PGW will update the database that I should not send the packets to the serving gateway any longer. Right? A11 registration active start. Active start means now the packets can flow. Because the GRE tunnel has been already established. So we should be able to resume our data transfer. So from the outside world, when the packet comes in at the PGW, then it should be able to send the packet to the HRPD serving gateway and serving gateway to the RNC all the way to the UE. So packets can now flow because the proxy binding has been updated. So that's the indication as far as RNC is concerned. Since the air interface is okay and the proxy binding has been updated, RNC tells the MME that handover is completed. There is the notification request on S101. That air interface is okay, the core network connection is established. So this is the acknowledgement. And since the UE has already gone into the EV-DO area and we have all the connectivity with the UE through EHRPD, there is no point in holding on to the LTE resources, and that's why MME is asking the E node B to release the UE context. So now E node B will forget about the UE. It will release CRNTI, the radio bearers, the GTP tunnels, everything it will now release for that UE. So that's how we can do handover from UE going across the technologies, from LTE to EV-DO in this example. Now, if you have done the pre-registration, this is very, very fast, right? Because we did not waste time in negotiating sessions. See, the only thing we did is we set up the traffic channel, we set up the radio connection, that's it. So, if you do this kind of optimizing handover, then we can have the target delay met. So 300 milliseconds is the target delay for handover for real-time services. So if you go from LTE to DO, then if you have optimized handover, just like what we discussed here, then we are okay. Then we can meet that kind of delay requirement. But of course, if you do not have this pre-registration done, if you do not have S101, then when you go to the new technology DO, you have to start over, you have to negotiate the session, it will take several seconds. So then we cannot meet the delay requirement. So the 300 milliseconds is for optimized interworking. Cannot meet that for non-optimized. We have some question. We need some more explanation on the trigger threshold for active handover and idle handover, EHRPD to LTE, etc. Okay, so let's do this. So let's cover all the scenarios first, and then we will come back to that question, okay, to make sure we cover all the aspects of your question. Okay, now going from E-U-TRAN to EHRPD in the idle mode. So what we discussed so far was connected mode. So we had handover signaling, etc. But this is salary selection. U is in the idle mode. So how do we do that? So here are some basic principles. So basically, the UE in the LTE system has no RRC connection because it is in the idle mode. So it is looking at system information by periodically waking up, so-called discontinuous reception. So the UE goes to sleep. The UE wakes up here. Okay, so periodically it wakes up and checks for page message, things like that, if things have changed, if it has crossed from one cell to another cell, etc. So that is the idle mode, discontinuous reception. I hope you are not doing discontinuous reception. You are supposed to do continuous reception. So that's the DRX from the LTE perspective. So basically we can during the sleep mode, we may not really be sleeping. We may indeed be looking for other technologies such as EV-DO, etc. So this is time off. When you say sleep, it is really time off from the LTE interface. But maybe we are looking at another carrier frequency LTE, other technology, depends, a lot of things. The parameters for cell reselection are specified by the serving cell, and that information is in SID number 8. So for LTE to EV-DO cell reselection, idle handoff, the parameters are inside SID number 8. So for example, you would see RSRP threshold here. You will see EC or I not threshold for DO. So those parameters are inside SID number 8. That is part of answer to your question. Then let's see. Yeah, in the idle mode, this is what we have, cell reselection. It does not matter optimized or non-optimized. In the idle mode, we will be doing the cell reselection. Okay, now let's take an example of cell reselection scenario. UE is in the idle mode in LTE, but this is optimized. So optimized meaning in the past, we had done the pre-registration with the EHRPD system. So we have some kind of session already available, already dormant, already negotiated. So then when the UE finds better DO than LTE, meaning RSRP will be very, very weak for LTE, and EC or I know from the DO sector is strong. So then UE makes this cell reselection. So UE reselects the cell, and that it makes a cell reselection decision. So as part of that, it says, okay, now I will stop looking at LTE. I will start observing EV-DO technology. So since you are already in the EV-DO area, you have to tell the EV-DO technology that you are in the EV-DO, so that in future the page message can be sent by the EV-DO system. So that's why we have to indicate the technology here, EV-DO. So there is an infrared mobility indication message. The UE sends a message that I have changed the technology. That is message, EV-DO message, infrared mobility indication. The network will send the acknowledgement, and now network knows that this UE is in the EV-DO technology area. RNC will update the HSDW that, oh, tunnel mode is 0. There is no tunnel between MME and HS, MME and S101. S101 is with RNC. So we will tell the HSDW that there is no need to work with the UE through tunnel, because UE is no longer in the LTE area. If UE is in the LTE coverage area, we have to use tunnels to communicate. But UE is no longer using any tunnels. UE is directly using EV-DO technology, EV-DO air interface. That is the reason HSDW is telling the PGW that let's update the binding. Because so far, PGW knows that packets need to go to the serving gateway. Remember, when the UE is in the idle mode, we still maintain the S5, S8 connection. When the packet comes from the outside world, we would send that to the serving gateway so that we can eventually send a page message using the help of MME. So PGW so far knows that it is supposed to send an incoming packet to the serving gateway, but now UE is no longer in LTE coverage area. That's the reason that we are telling the we are telling the PGW that please update your binding. Do not send packets to the serving gateway. So in future, when the packet comes in, the PGW will inform the serving HRPD serving gateway. Then we would send page from the EV-DO destination. So in summary, cell reselection means the UE based on the thresholds that it got from the LTE node B would make the cell reselection decision. LTE is becoming weaker, DO is becoming better, so then it made this kind of cell reselection decision. Okay, time for a question. I'll give you about a minute. How does the UE know neighbor list, EV-DO neighbor list? Oh, maybe I should further clarify. Assume that UE is in the idle mode, okay? Idle mode. UE is in the idle mode. Idle mode. In LTE. Not connected. So UE is in the idle mode. In the idle mode, what tells the UE the EV-DO neighbor list? 10 seconds to go. Okay, SIB number 8. That is the correct answer. System information block number 8. So that tells the UE who are the EV-DO neighbors, which are the PN offsets, what the frequency band it is, things like that. Okay, one more question. Okay, now this is a connected mode, okay, handover. Handover means connected mode. Cell reselection applies to idle mode, but here we are talking about connected mode. The UE has radio connection with the EU trans. So who tells the UE to go to the EV-DO sector? Where is the handover algorithm implemented? Ten seconds to go. Okay, E node B is the correct answer. The measurement reports are processed by the E node B. E node B looks at the ECO node for DO, RSRP, RSRQ for LTE cells, and then it makes a decision that yes, you should go to this specific EV-DO sector. That is the handover decision made by E node B. E node B has the handover algorithm implemented. So when we go from LTE to EV-DO, LTE is the source technology. Source makes the decision. So LTE makes the technology. LTE technology makes the handover decision, and of course within the LTE, E node B is the one that has handover algorithm. Okay, now we'll take care of a couple of other scenarios. One scenario is the UE powers up in EV-DO. Then what happens? So far we looked at following. We looked at what happens when we power up UE in LTE. Then UE goes from LTE to EV-DO, connected mode, idle mode. So we talked about those scenarios. Now we will go the other way. We power up in EV-DO, and then UE will go from DO to LTE. Those are the next set of scenarios we would take care of. So let's say we power up the UE in the EV-DO area, then what happens? So then we have to have the connection between the UE and base station, there is the radio connection, and then we have the session. Radio connection, we allocate MAC index to the user. MAC index. Session, we give UATI. RNC gives UATI to the user. And as part of the session setup, we negotiate a lot of parameters. So it may take several seconds to negotiate a session, EV-DO session between UE and the RNC. Now device authentication is optional, but if we do want to do that, it is possible. We will use the A12 interface between the RNC and ANAAA server to authenticate the hardware device. So let's say that is done. Then location update, telling the UE what area it is in. So color code, things like that will be conveyed to the UE. Then the RNC will do the A11 registration with the HSDW. That okay, we need to set up the connections. Remember main connection, service connection, auxiliary. So we are setting up the main service connection. So we are doing the registration as part of the PPP setup between the UE and the HSDW. We say, okay, let's use if protocol. And using the if protocol, we move forward and take care of the authentication. So that is between the UE and the HSDW and the AAA server. So once the authentication is done, then we have to get the quality of service related information, and we need to give the IP address. So vendor-specific network control protocol will be used to connect to a PDN, packet data network, and to allocate an IP address to the UE. So this is what we'll do in step 8. Now we need to get quality of service information. So the PCRF, policy and charging rules function, that would dictate QS parameters to the HSDW. Once that is done, then we have to tell the PGW that let's update the binding, because right now the UE is in the DO coverage area. So the packet should be coming to the UE via EV-DO. So that is the reason HSDW does the proxy mobile IP binding with the PGW. Now, as part of that, the PGW allocates an IP address to the UE, which will find its way to the UE through HSDW. Okay. Now we will focus on specific aspects that are new to the LTE video interworking. So let's discuss the authentication process. As part of the PPP negotiation, we will say, okay, let's use the authentication protocol C227 that corresponds to IP. So in the link control protocol, which is part of PPP messaging, this configure request has this identity of the protocol. So UE says, okay, I acknowledge that we will now exchange IP messages. The HSDW sends IP request asking for the identity of the UE, and the UE will send identity network access identifier. So this is something like John at Verizon.com, something like that. There is some kind of network access identifier in the form of an email address type address. HSDW tells the AAA server that here is the identity of the user. So give me the authentication parameters. So AAA server works with the HSS to create those parameters. So this is the random number, authentication token, message authentication code. The challenge that goes to the UE includes the random number, authentication token, and message authentication code. The response is not sent to the UE because we have to let me see if I have any. Yes. So a UE is sending the challenge to the HSDW. So what is happening here is first UE authenticates the network. So in the challenge, we have the random number token and message authentication code. So they go to the UE, and the UE will put the random number into the authentication algorithm, and it will generate the codes. Let's say authentication token, message authentication code. It will confirm that the token is matching what the network is saying. If they match, it is talking to a valid network. So this is just like LTE authentication. A message authentication code, we just make sure that the message is integrity protected. So message authentication code, we just confirm that whoever sent the signaling message is a valid entity. Now, toward the end of the process, we create a master session key, which would be used to generate some additional keys, or pairwise master key, and so on, so that eventually, if we want, we can encrypt signaling messages, we can encrypt user traffic, and so on. So far, the user has authenticated the network, but now we have to move forward, and network has to authenticate the UE. So for that purpose, the UE is sending in the if response the challenge, aka challenge, and it includes the response. HLCW will then talk to the AAA server and send that information, the response, to the AAA server, and the AAA server would compare the response it got from the HLCW with what it expects, whatever it expected response. So if both of those match, then this is a valid UE. So now the AAA server has authenticated the device. Also, the AAA server will generate master session key. It would be generated, and some additional keys are also created. And basically, we send that information in the if success message, along with the if success message to the HLCW. So HLCW now stores that key so that it can create additional keys for future encryption. In the notes, we have given you additional parameters in terms of keys. So if success going to the UE, it means the overall process of authentication is now success. So this is how we can do mutual authentication now in eHRPD. See, normally in video we have the network authenticating the UE, but now with LTE and eHRPD we have mutual authentication. The next few minutes we will talk about how to allocate an IP address to the UE. Okay, now IP address, the standard has many approaches, so we have given you examples of several approaches. We support both IPv4 and IPv6. We are moving away from client mobile IP, and now we have started using proxy mobile IP. The reason for that is UE is much simpler. UE has no role to play in IP mobility. You doesn't have to worry about that. That is the reason that we are moving away from client-based mobile IP. Now, if we want, we can use DHCP approach or vendor-specific network control approach, but I expect this to be much more popular. And how do we get IP address? Basically, UE will be talking to the HRPD serving gateway. HRPD serving gateway will be talking to the PGW so that we can allocate IP address to the UE. You will see that IPv6 is becoming quite popular, and basically IPv6 we have 128 bits for the IP address. Compare that with only 32 bits for IPv4. So we have so many IP addresses that I have heard that with IPv6 addressing, we can address every single grain of salt on our planet. many IP addresses. Another number I have heard is 50,000 IP addresses per square meter of surface area on the planet. So lots and lots of IP addresses. So do not worry about running out of IP addresses in the near-term future. That is one of the motivating factors behind IPv6, because IPv4, we are running out of those public IP address space. IPv6 will alleviate that problem. Not only that, IPv6 has built-in authentication encryption mechanism. We have built-in support for quality of service. In the IP header, we can put the DSCP itself, differentiated services code point, so we can easily provide quality of service. Another beautiful feature of IPv6 is auto configuration. So the UE can automatically create its IP address based on some information received from the network. Okay, so let's take an example of how to give IP address to the UE. And what we would do, we would discuss from the IPv6 perspective. Now, as I mentioned, we are moving away from client-based mobile IP. We are moving to the proxy mobile IPv6. So this is our PGW. It acts as a local mobility anchor. And this is our HRPD serving gateway, mobile access gateway. So for this UE, we give some IP address that is given by this PGW. So this PGW will give mobile node so-called home network prefix. Okay, home network prefix. So basically, we have two parts of the IPv6 address. We have the network prefix and we have the interface ID. Interface ID, 64 bits here and 64 bits here, total 128 bits. So we are giving the UE some home network prefix, the initial portion of the IPv6 address. Another UE we have given another home network prefix, that's possible. So PGW will give those home network prefixes, the network prefix portion of the IPv6 address. Separately, the PGW will also give interface ID. And then the UE will combine the two, network prefix and the interface ID together to create its own IPv6 address. So when the user goes from, let's say, one area to another, let's say one mobile access gateway to another, it can keep using same IP address. Because the IP address was allocated by the PGW, the local mobility anchor. So your PGW will not change. So for a given user, PGW remains the same. And because of that, we have this proxy mobile IP tunnel. If the user goes from, let me draw another picture so that it's clear. So we have one serving gateway, another serving gateway, and this is our PGW, local mobility anchor, mobile access gateway. So our UE has IP address X, which was earlier given by this PGW. So now, if the user goes into another area controlled by another HSDW, then the only thing that is changing, same IP address, the only thing that is changing is the tunnel. So we are changing the tunnel. That's it. Our PMIP tunnel is changing between two entities, PGW and HSDW. So our PGW remains the same. Our IP address remains the same. Here, the UE did not do anything. Within the network, we figure out that, oh, the UE has gone into HSDW2 area. So HSDW and PGW, they will work together through proxy mobile IP signaling so that we can change the tunnel endpoints. So this end of the tunnel is the same. Tunnel end same. The only thing that is changing is the other side of the tunnel. So we are changing only one side of the tunnel. So that is the beauty of proxy mobile IP. That UE doesn't have to worry about anything. We can maintain the same IP address as we go from one big city to another big city. Okay, so let's see how to give the IP address to the UE. So basically, we will be relying upon the new protocols, vendor-specific network control protocol, to provide IP address to the user. So let's talk about that. Okay, so remember we are in EV-DO area. EV-DO area. Okay, remember one thing, PGW will never change. So if you go from one PGW area to another PGW area, then you are in trouble. But that will not happen. In LTE EHRPD, PGW does not change. So do not worry. PGW is the same. Okay. But now, how do we give the IPv6 address? So our UE has sent this message, configuration request, vendor-specific network control protocol. So it says that this is the initial attach operation, so I need an IP address, and please give me IPv6 address. HRPD serving gateway will tell the PGW that I need IPv6 address for a UE, so that is in the proxy binding update. In the proxy binding acknowledgement message, we provide network prefix and we provide interface ID. So proxy binding acknowledgement has both the parameter interface ID and the network prefix. However, we only forward the we only forward the network, not network prefix, but the interface ID. We forward only this interface ID. So we keep network prefix here. Do not send to UE yet. We only send interface ID. So that interface ID is reaching the UE here. And we said, okay, that is for a specific packet data network. Let's say packet data network number, let's say 8. So acknowledgement says, yes, I received the IP address, interface ID for packet data network number 8. So now, up to this point, the UE has received a part of the IPv6 address, only the interface ID. So if the UE wants, it can create its own IP address. It can use its own link or network prefix. Because that is the idea behind IPv6. We want UE to create its own IP address. However, for LTE and EV-DO now, we have one more step. The UE may send router solicitation message, or autonomously, HSDW will send a message, router advertisement. And now inside that, we provide this network prefix. So the UE will now combine the IPv6 interface ID and the network prefix. And combining the two yields a full-fledged 128-bit IP address. So this is how we give IP address to the UE. In terms of quality of service, when we go between two technologies, we have to do the mapping. For example, in LTE, we have quality of service class indicator. This is what we have, and we have 9 levels of QoS. Remember, we have guaranteed bitrate, maximum bitrate. In EV-DO, we have flow profile ID, okay, and the flow profile ID quantifies quality of service. and there are lots and lots of descriptions. And I will give you one example. Let's say LTE has a QCI number 1. So we can say that, okay, what kind of bearer? Do we have to guarantee data rate? Yes, we have to guarantee data rate. How much data rate? Let's say 32.8. That corresponds to flow profile ID hex number 100. So when we go between two technologies, let's say from LTE to EV-DO, so in that case, HSGW, HRPD serving gateway, will do the mapping, because the HRPD serving gateway knows about LTE QoS, it knows about the flow profile ID. It says, oh, if my data rate in LTE is 32.8, I have to guarantee that it is QCI 1, I have to guarantee 100 millisecond delay, I have to have 1% packet error rate. That means that specific bearer has to be mapped onto flow profile ID number 100. So in summary, in the standard we have a long table with lots and lots of entries like this. So HSGW will do the mapping between LTE QoS and eHRPD QoS. Because in LTE and eHRPD we are supposed to provide quality of service. So we have the recommended mapping from the start. Okay, now in terms of quality of service, how do we set up the bearer, etc. So basically what will happen is to implement QoS, let's say I have some kind of SIP signaling. Okay, and as part of that I need certain QoS. So the SIP signaling message will find its way to the PCRF. Okay, PCRF will create the rules, and those are the rules it is giving right now to the HSGW through the XA interface. Now HSGW says, oh, I need to provide QCI 1, I need to provide guaranteed bit rate, X kilobits per second, etc. It will map that onto some flow profile ID, and it will tell the UE as part of reservation message that, okay, we need this kind of QoS. So then between the UE and the RNC and the HSGW, we have the A10 connection. This is for traffic to meet a new QoS. Then we have to have auxiliary service connection. Remember, auxiliary service connection, that's for different QoS. So we have the reservation messages exchange between UE and the HSGW that, okay, this is the flow number that we have. We identify the flow by certain traffic flow template. Traffic flow template, it will have IP address, port numbers, etc. to identify the traffic. Once the reservation is done, the confirmation message is sent, and then we turn on the reservation. So we activate the flow at this point. And now the air interface is ready because we have set up the auxiliary service connection. The connection between RNC and the HSGW is ready, and of course we would have the connectivity between the HSGW and PGW, that is the GRE terminal here. And here you have to use DSCP for quality of service. Mobility from eHRPD to LTE. Okay, so right now we are in the DO coverage area, and then we want to go to LTE. Now here is the basic, most important concept. UE has to be in the dormant mode in LTE. In EV-DO. You cannot have the UE with radio connection and then going to LTE. We must finish up the data transfer first in EV-DO. There should not be any data transfer for some time. It means after data inactivity, the radio connection would go away and UE in eHRPD enters dormant mode. Now we can go to LTE. So we must have UE in the dormant mode in EV-DO. That is the prerequisite. Now, once that is done, then UE autonomously there is no directive from anywhere. UE autonomously makes decisions to go to LTE. Now, this is all implementation specific, proprietary. So chipset itself would decide that, okay, maybe I should go to LTE. Perhaps it found a better LTE cell compared to EV-DO, EC or I0. So UE autonomously makes the decision. It sends the attach request to the MMA. Another very important point. In the attach, it does not say initial attach. It says handover attach. And the reason for that is UE already has the IP address. It got the IP address from PGW when it was in the EV-DO area. So when we say handover attach, it is an indication to the PGW not to give a new IP address. Otherwise, we would lose existing IP connectivity. Now, we can do authentication. We set up the bearer. SGW tells the PGW, let's create a new bearer, and there is a handover. So no need for new IP address. We already have an IP address for the user. So we just update the entry. So once the bearer request message, this is for GTP based tunnel. This is more popular. So you can expect this to be more common. Do not worry about this. It is correct, but in the commercial deployments, we are seeing more of this kind of configuration, GTP based. So create bearer request will have this information that there is no need to give new IP address. It's handover, and the access technology type is LTE, not EV-DO. Once that is done, then we create the connectivity with the PGW through SGW. So now we have set up a new bearer with the UE. Since UE has already gone into the LTE area, then we will have to set up all the additional PDNs. So we may have VGW.com, BlackBerry.net, so whatever additional PDNs we want to connect to, we can do that. And now we have to release our EV-DO resources, because UE is already in LTE. So no point in holding on to EV-DO resources. That is the reason the PGW is telling the HSW, please cancel the binding that we have right now. So there is a binding, revocation, indication, and acknowledgement. So now onwards, HSW does not expect packets from the PGW, because PGW will be forwarding the packets to the serving gateway. UE is in the LTE system. We tell the AAA server here that let's end the control session, because user is with the LTE system. So HSW doesn't need to worry about that. Once the timer expires, maybe few minutes or whatever, maybe UE will come back. So if UE does not come back in a few minutes, the timer expires, and then we would send lifetime 0 in the registration request message. So at this point, we lose all the links within the EV-DO system. Okay, so today we talked about how LTE works with EV-DO. So basically, we have new interfaces. We have S2A interface, that is HSGW and PGW interface. There is the proxy mobile IP based tunnel, GRE tunnel, and that will make sure that we can have seamless mobility between LTE and EV-DO, and within the DO system, one HSGW to another HSGW. S103, this is for packet forwarding, going from LTE to EV-DO, and HRPD pre-registration, handover signaling. You can do that through MMA RNC interface, and this is for optimized mobility. This is one way optimized handover from LTE to EV-DO. If you do pre-registration, that will help your handover to be much faster. and you can meet 300 millisecond delay requirement for the change in the radio access technology. IP address, again, PGW is anchoring the IP address regardless of what radio access technology the UE is using. Could be LTE, could be EV-DO. We have support for IPv4, IPv6. We give an example for IPv6. And we are moving away from client-based mobile IP in EV-DO. We have started using the proxy mobile IP so that UE does not need to worry about anything. Okay, that's what we have planned. Give me 1 or 2 minutes because we had a question on the interworking style selection parameters, etc. So I would give you a 1 to 2 minute view of that, and then I would let you go. Okay, so basically from LTE to EHRPD. So that could happen in the connected mode or in the idle mode. Okay, so we will use SIM number 8 in the idle mode to give the neighbors for EV-DO, and we will give the thresholds, cell reselection thresholds. So if LTE drops below some thresholds, that would be RSRP, then EV-DO, if your I0 is above some other threshold. Those kinds of thresholds are given in SIM number 8. If the UE is in the connected mode, then basically here we can provide the neighbor list, we can provide measurement gaps, so UE can make measurements of other technologies such as EV-DO. The UE will send a measurement report when events B1 or B2 or both occur, and based on that, the eNode B sends the handover command to the UE to go to other technology. And in that case, we have S101 optimized handover, if you support that. The other way, going from EHRPD to LTE, basically this is all implementation specific. Okay, so UE can decide on its own when it wants to go to the LTE. However, the prerequisite is UE has to be in the dormant mode. There's the prerequisite. Okay, thank you very much. Sorry, we took 5 more minutes than intended. Shall we send the evaluation form to the students?
Yes, I'd like to thank everyone for participating, and of course thanking Nishish for his presentation today. He is going to send his whiteboard notes to us, and we're going to pair that with his annotated PowerPoint that he used today, and we will forward that to everyone on the session today. Right now I'm putting up the end of course evaluation, and if you haven't already done so, please put your computer in full screen mode by pressing F5 on your keyboard. And it's very important at the bottom of, at the bottom of the survey, please click on proceed when you've finished. And when you have finished, please drop the bridge so we know that you're done. And again, your information and feedback is very vital to us, so we appreciate you filling this out. It looks like we're having a little bit of problem getting that up there. Okay, it seems like it's coming up now. Hold on a second.
Yeah, I can see, so at least,
okay.
Yeah, I can see that.
So very important, make sure you're in F5, and of course, very, very important, click on the proceed button when you have finished. That allows your survey to be completed. We will keep the survey up after we close the bridge, but we do ask if you could take the survey now and log off of live meeting. We'll know how many people still need to take the survey. So thank you again, Nishish.
Oh, thanks for your questions. I'm still here for a few more minutes, so feel free to send additional questions through Q&A. And again, you will get the class notes from me. You will have my email address, so email address is also fine if you have additional questions. If you are going away, then we will talk to you tomorrow morning on for another session.